Line Integrals Part 1. Let f be a scalar-valued function defined over a curve parameterized by arc length s. What is the area of the curtain that hangs from the surface of f over the curve? Notice that over the curve, the function can be defined in terms of the arc length of the curve. The area of one rectangle for a given value of s is the height of the surface times an infinitesimally small arc length. Increasing the number of intervals while letting the arc length go to 0, we find that the area of the curtain is given by this line integral. A better name for this might be a curve integral. And an example of using a line integral would be to find the average temperature along the edge of a plate. First, we parameterize the curve by arc length s. Now we define the temperature in terms of s, so we're looking for what is the temperature on the edge of the plate, because the edge of the plate is our only area of interest. After we do that, we set up the integral to find the average value of the temperature on the curve. The average temperature will be 1 over the length of the curve, which in this case is 2 pi, times the line integral. And then we integrate. We break 2 sine squared into a sum of sine squared plus sine squared, and then use the Pythagorean theorem. Next, we use the power reducing formula for sine squared. After we use the power reducing formula, we distribute a factor of 2 into the parentheses. Clean up the integrand, and then go ahead and integrate and evaluate. So the average temperature on the edge of the plate is 150 degrees. What if arc length is not the parameter, but rather the curve is described generally by t? Then we can find the line integral using this formula, which makes use of the fact that ds is equal to speed, ds dt, times dt. And that speed, ds dt, is just the magnitude of r prime. And we're going to use this to look at an example in your homework. Find the average value of f on the cubic x equals y to the 3, with y going between -9 and 9. First, find a parametric description of the curve. Here is a parametric description of the cubic. And now compute r prime. R prime is 3t squared, 1, and then the magnitude of r prime can be found using the Pythagorean theorem. Next, use the parametric description to make substitutions in the integrand and set up the integral. F in terms of t, so this is the surface over the curve, is given in this manner. And we're ready to integrate. We substitute for f, we substitute for the magnitude of r prime. We notice that t is running between -9 and 9, and then we integrate. The average value would be this integral divided by the length of the curve. Now this integral, when you first look at it, looks fairly difficult, and in fact it would be very difficult to find the antiderivative. But in this particular case, the integrand is odd. Since the integrand is odd and the bounds are from -9 to 9, the integral is 0. And that's because the area under the curve is 0 because of that symmetry. So that means that the average value of our surface on the curve with y going from -9 to 9, that average value would also be 0. Let's evaluate this line integral where c is the line from P to Q. As before, we need to find a parametric description of the curve. Now, the curve is the line from P to Q. We need to have a parametric description of that line. First, we find the displacement vector from P to Q. Then we use the displacement vector and the point to find an equation of the line. And so here's our parameterization. Now, given our parameterization, we're ready for step 2, and that is to compute the magnitude of r prime. So we find r prime and then we find its magnitude. And now set up the integral using the parameterization. Well, if t is running between 0 and 1, that's our bounds. R prime is the square root of 3. And now I need to write f in terms of the parameterization. After I do that, I clean up that integrand and then integrate. And so the line integral from the point P to Q is 7 radical 3 over 6. Take care, and I'll see you in part 2.